Hair plays a significant role in our appearance. It defines our personality and shapes people's impression on us. For this very reason, nowadays, we manage our hair not only for personal hygiene, but also for fashion and style. And surely, chemistry plays a vital role here.
Hair management is one of the crossroads of arts, fashion, health, and science. In this project, we will be standing on behalf of chemistry and investigate into the chemistry that cleans our hair, colors our hair, and shapes our hair. Along the way, we will uncover some weird sciences that enable our hairstyle to come true, and how some of the world's most ingenious yet simple chemical principles have created a multi-billion-dollar industry. Last but not the least, we will point out whether the hair industry as we know it is a sustainable solution, personally and environmentally.
However, before we begin, we should take a glimpse of what hair actually is chemically. Understanding this helps us to choose the right chemical and the right reaction for cleaning, coloring, and fixation of hair.
Hair, like skin, is composed primarily of fibrous protein. To understand the properties of hair, we must first understand what proteins are. Proteins serve as a structural material for us, including our hair. Like plastic, proteins are polymers. However, they differ from other polymers in that the monomers unit are about 20 different amino acids, and amino acids differ in their side chains. In the monomers, there are two functional groups. The first one is the amino group, which is essentially NH2, and another one is the carbonyl group, which is COOH. Both functional groups are attached to the same carbon, which is called the alpha carbon. The other two lone pairs of the alpha carbon is bonded to R and H in the simplest form of amino acids.
However, this is not the end of the story. The carbonyl group is acidic and amino acid is basic. The two functional groups interact according to the Brons-Lowry acid-base theory, an acid transferring a proton to base. The resulting product is an inner salt. This compound has a negative and positive charge part, each on one end. This special property of amino acid enables the invention of shampoo. The protein in our hair is called keratin. It bears all the properties mentioned above. It is a tough and insoluble polymer that makes up not only hair, but also our nails and outer skin.
Amino acid chains in our hair are held by four forces: hydrogen bond, disulfide linkage, salt bridge, and dispersion force. When we're talking about hair cleaning and fixation, we're essentially playing with these forces.
Dispersion force exists between all molecules, so logically, it appears between our hair too. As electrons revolve around the nucleus, momentarily negative charged areas are formed. These areas are attracted towards partially positive charged areas. As our hair has long chains of amino acids, the probability of having uneven electron distribution is high. Though, this dispersion force is weak compared with others, so it is no significance when we're trying to shape, fix, or clean our hair.
In general, hydrogen bonds are formed between highly electronegative atoms. Hydrogen will strongly bond with highly electronegative atoms such as fluorine, oxygen, and nitrogen with lone pair electrons. In keratin, there are C double bond O and NH2. NH2 in one amino acid will form a hydrogen bond with oxygen in C double bond O in another amino acid in our hair. These bonds are very strong and give the shape to our hair. These bonds can be altered by water, which also forms hydrogen bonds. This opens up a whole new world of opportunity for aqueous-based hair fixation technique.
Subbridge here refers to ionic bond, not the subbridge in photonic cells. It exists between amino acids. Subbridge accounts for 35% of the strength of the hair and around 50% of the elasticity. Due to the numerous ionizable side chains of amino acid found throughout the protein, the stability of protein depends on pH. In extreme pH conditions, the constituents which are responsible for the ionic bond may lose its ability to do so. It is a crucial point to look after when designing shampoos. Disulfide bond is a covalent bond, usually derived by the coupling of two thiol groups. Thiol is a functional group with RSH. The disulfide bond is strong, with a typical bond dissociation energy of 60 kilocalorie per mole. Because of this is what we want to play with in permanent hair waving or straightening.
When you walk down the aisle of a supermarket, we see a plethora of shampoos. Shampoo proclaims that they not only clean, but also energize and revitalize. It seems like magic, right? No. All the shampoo you see are based on the same basic mechanism.
Shampoo can clean hair. No doubt, it's not a difficult mission. All that is required is a removal of a thin layer of oily material known as sebum, produced by sebaceous glands in the skin. It coats and protects the hair. Unfortunately, sebum also acts as a virtual magnet for dirt. Since oils are not miscible with water, washing with water would not do good.
Prime ingredients in all shampoos are substances called surface active agents, or surfactants for short. Such molecules have a dual nature. On one hand, it is considered as ionic, so it is polar, giving it a hydrophilic property. That means it is water attracting, which is also polar. The rest of the molecule is like a typical hydrocarbon. Since the electronegativity difference between C and H is small, so on furthest end of the molecule, it is nonpolar, giving it a hydrophobic property, which means water repellent. All these means that one end of the molecule dissolves in water, while the other end of the molecule dissolves in nonpolar substances such as oil. During cleaning, the molecules in shampoo arrange themselves in a spherical manner, with the nonpolar hydrocarbon ends sticking towards each other. The ionic heads stick outward and repel each other. So, a spherical shape is formed called micelle. The dirt and grease in our hair will then stuck inside the sphere and carried away by washing.
On the other hand, surfactant molecules wedge between water molecules, reducing surface tensions and allow water to flow easily into every pore on a surface. Foaming is a byproduct of this process due to the reduced surface tension. There's no clear linkage between the ability to foam and the ability to clean. Good surfactants can produce virtually no foam, but they don't sell well. So in the end, foaming is mostly a marketing consideration.
There are many kinds of surfactants out there. Soap is the earliest surfactant invented. Soap is a sort of long-chain carbonic acid. The soap doesn't work well with hard water, water that contains certain metal ions, in particular calcium and magnesium. Soap and ions react with these metal ions to form a soluble substance. One solution is to use soft water with help of water softeners. Another approach to this problem is to use the synthetic detergents. Their calcium salts, unlike soap, are soluble and does not separate out even in hot water.
If it is just surfactants, why there are so many kinds of shampoo? Shampoos for different kinds of hair, oily, normal, and dry, are essentially different in terms of concentrations. Oily hair needs higher concentrations. Another point that is advertised are flavors and fragrance. These have nothing to do with the cleaning ability.
Last but not least, shampoo differs in terms of pH value. As mentioned before, the salt richness in hair can be affected by pH. Therefore, it stands to reason to say that shampoo's acidity affects. Hair is slightly acidic. High pH value, alkaline, can cause a removal of proton from the amino group. Acidic environment causes carboxyl group to gain a proton and lose charge. In both cases, the salt bridge is weakened considerably.
Conditioners. Using applied after the action of shampoo has nothing to do with cleaning. One of the major purposes of it is to reapply some clean sebum to hair, which is removed when using shampoo. After all, this sebum is essential in protection. This is one of the reasons why conditioners cannot be mixed with shampoo into one single mixture. They have opposite effect on hair. Another purpose of conditioner is to enhance smoothness with sebum. This way, friction is minimized between hair and charging by induction, which introduces electrostatic repulsion between hair can be minimized. Conditioners also enhance appearance, tactile perception, and physical integrity of hair.
The hair fixation technique is mainly used to achieve different kinds of hair styling. As the standard of beauty changes over time, the demand on hair fixation technique varies. As we are interested in the chemistry of our hair, I shall introduce the fixative processes we encounter in our everyday lives.
Hair fixative techniques are classified into two main categories, which are temporary and the permanent hair fixation. The chemical principles behind these two kinds of techniques varies, and so as the effects.
As all of us had expected, water itself can act as a method of temporary hair fixation. When the hair gets wet, the C double bond O and NH2, which originally are bonded hydrogenly, are disrupted by the water. The water acts as a new bridge. Due to the strength of the hydrogen bond, when the hair is wet, we can shape it in any ways we want it. However, this method is as temporary as it can be. Once the water is evaporated, such effect is lost.
Early in the ancient Egypt dynasty, methods of hair fixation have developed. The ancient Egyptians generally wrapped their hair with the mud from the hot spring around wooden sticks and curled their hair with the sticks. They dry the mud on the sticks under the sun and remove it later.
In 1938, Willett invented the cold waving technique that was a precursor to the modern permanent waving technique. And in the 1970s, aerosol foam Mousses, which are styling products similar to those we use nowadays, were invented.
The temporary hair fixative techniques basically involve the reaction between hair and hair fixative products, as a result affecting the intermolecular interaction between two reactants. And the temporary hair fixations. Hydrogen bonds and ionic bonds are affected by styling products. The following table shows 9 common styling products that provide temporary hair fixation. Aerosol foam mousses, also known as hairspray, is a multifunctional styling product. It can be applied both on wet and dry hair. It can be washed out or left in hair. It is effective, and it can save hair from being sticky and stiff. The big idea here is that hair can be held in place by using resins, solid or semi-solid organic materials. The particles in these substances have stronger intermolecular force than the four that are present in hair, that overcomes the force between hair and shapes it, temporary.
Common resins used on hair are polyvinyl pyrrolidone, or PVP. The resin dissolved in the solvent and sprayed on hair. Then the solvent evaporates, leaving the resins. The solvent or propellant is usually short hydrocarbons, thus volatile. Resin is also available in mousses. A mousse is simply a foam. The active ingredients is still those mentioned above.
For example, the aerosol foam mousses generally contain mainly water, as it is the best solvent to mix various chemicals. Alcohol acts as a co-solvent, as it could help to dissolve organic chemicals and help producing quick breaking foam. Thirdly, it contains polymers or resins that contain tetraamine groups. The polymers or resins are the most effective and important functional components. It acts as the conditioning and fixative agent.
Plasticizers and conditioners are also involved in the content list of aerosol foam mousses. The amount of these two ingredients determines the manageability and fixative properties of hair and the stickiness of the spray. On the other hand, the propellant determines the aerosol foam's texture, stability, and also the physical property. Experiments have shown that small bubbles would present in the foam if halogenated propellants are used, while propellants of hydrocarbons would increase the stiffness of hair due to the non-polar nature of it.
You may wonder why the alcohol only acts as a co-solvent while it could dissolve both organic chemicals and the chemicals that contain hydrogen bonds. It is because alcohol performs dehydrating properties that will dry out the hair and remove natural lipids in the hair. Large amount of alcohol is therefore not appropriate.
You may also wonder why aerosol foam Mousses can perform multi-functions while only consist of a kind of liquid. It is because the polymers employed in Mousses are positively charged, as the tertiary and amine group are potent. The cationic property of polymer enables it to be blended with non-ionic or anionic film formers like monoester of poly to give a firm hold. Therefore, the conditioning and fixative properties could be conferred simultaneously.
When formulating hairspray for temporary hair fixations, we have a few points that we must pay attention to. First, the aesthetics of foams and the product's performance, such as stability and stiffness. Moreover, we should consider the VOC content that consists in the product. VOCs will react with sunlight to form unwanted ozone in the lower atmosphere and will contribute to the formation of ground-level ozone or smog. In order to be morally accepted and ethical, styling products with low VOC content are recommended.
In order to reduce the contents of VOC, water is usually added. However, this would create the potential for can corrosion, which exponentially increase as amounts of water increase.
We have been talking about temporary hair fixation. As for permanent hair fixation, there are basically two kinds of chemicals. The first one is thioglycolates and the second one is bisulfides.
As mentioned before, our hair is comprised largely of alpha-keratin proteins. The properties of protein are mainly dependent on the presence of disulfide link.
In the first step of the permanent hair fixation, the hair is reduced by the reducing agent thioglycolic acid. The process is reversible and therefore does not go to complexion and is an equilibrium process. A thio reacts with the keratin in hair to form a mixed disulfide and a free keratin sustain.
The mixed sulfide further reacts with additional thio to give the disulfide of the reducing agent and another free keratin sustain, and a thiosulfate group too. The overall reaction is like this.
In fact, thioglycolic acid is not a strong reducing agent that makes it suitable to involve in the reversible reaction. In reality, you definitely want to increase the rate of reaction in order to boost the efficiency of the reaction. However, in this case, we would rather beg for a reaction that does not go into complexion. In practice, it is found from cases that our hair would not recover sufficiently when reoxidized if the hair was reduced beyond a certain point. This is definitely not allowable in commercial settings.
After our hair is reduced and the disulfide interactions are broken, our hair can then be curled or straightened. Our hair is later reoxidized by a mild oxidizing agent like hydrogen peroxide to reform those disulfide bonds in a different orientation. And then, done! Our hair is fixed permanently.
Although the kinetics of permanent hair fixation of the two kinds of chemicals, thioglycolic acid and bisulfide varies, the thermodynamics of the two processes are generally the same, that they both involve redox reactions. The mechanism of the two processes are complicated. I shall not introduce them to prevent causing confusion, as it can involve processes that classifies as pseudo-first order kinetics. Generally, we only know that the reaction rate is given by the following derivative, where B is the amount of sulfur-sulfur cysteine bonds involved in the reaction and T is the time taken.
To conclude, we can see that both temporary and permanent hair fixation are manipulation of bonds within our hair. Temporary fixation involves bonds like the relatively weaker hydrogen bond, and permanent fixation deal with stronger bonds like the disulfide linkage and stronger reactions like redox. The forming and breaking of bonds and intermolecular interactions form the basis of contemporary hair fixation techniques.
It is obvious that human hair color varies, but how? The color of human hair is mainly due to the presence of melanin pigments. In hair, the pigments are located only in the cortex. Basically, colors of blonde, gray, brown, and black in hair are due to the existence of eumelanin, and the colors of red and yellow are due to the pheromelanin pigments.
Some natural colorants have been used for dyeing hair for centuries and are still in use today. Henna is the most widely used colorant. It gives a strong orange or reddish color to the hair. Bleaching is probably the simplest method of changing the hair's natural color. Bleaching processes involve partial or total decolorization of natural melanin. The bleaching process is rarely done without the presence of an alkaline solution of hydrogen peroxide. Since hydrogen peroxide is most active at alkaline pH, it is usually stored in acid solution. When used, the peroxide is mixed with a base to give a final pH around 10.
There are two distinct steps that are involved in the process of bleaching. Firstly, it involves a fast dissolution step to disperse and dissolve isolated and melanin granules. The dissolution is followed by a significant color change from black to brown of the solution. Up to now, the chemical steps involved are unknown, but it has been argued that the dissolution must involve the destruction of various cross-links.
After the bleaching of hair, there is now a blank canvas which we can now add color to it. The most common way of adding color is called oxidation dyeing.
Oxidative dyes are dyes that allows permanent coloring. Color is produced inside the hair fiber by hydrogen peroxide. As hydrogen peroxide can perform bleaching effect, the oxidative dyeing would bleach the hair's melanin and shades lighter than the natural hair color.
As for the action of coloring, it is usually the result of amino and hydroxy aromatic compound undergoing oxidation. After a few oxidation and attacks of chemical, a final oxidized product is formed, also known as the indo dye.
Blue indo dyes are formed from mixtures P-diamines, M-diamines, or phenols. Red from P-diamines, P-aminophenols, and M-aminophenols. And yellow or brown indo dye from P-diamine, P-aminophenols, and resorcinols.
The intensity of the dye is controlled by the concentration as well as the application temperature. Also, by using salt of lead or substances like dihydroxybenzene, the reaction can be slowed down, leading to a progressive dyeing method. The substances stay in hair for a month or so and change in color slowly and naturally.
An oxidative dye formulation must contain the following ingredients.
Alkalizer. It is used to provide a preferable alkaline condition of pH 9 to 10.
Surfactants. It is helped to remove dye deposits on the hair surface.
Solvents. Most dye ingredients are only slightly soluble in water. Organic solvents like glycols and alcohols are needed to dissolve ingredients.
Antioxidants, like sodium sulfite. Some dyes are sensitive to oxidation. Antioxidants are used to prevent the formation of dark-colored products during manufacture and storage of product.
Chemistry plays a central role in the management of hair. As we can see throughout this video, simple yet ingenious chemical ideas enable us to clean, fix, and color our hair. Most chemicals aren't directly hazardous to our health, but does this mean we can use them however we want to? Of course not. These chemicals may be toxic to our environment, ranging from non-biodegradable synthetic substances to harmful gases from sprays. Understanding these chemical principles behind healthcare products helps us to choose and use these products more wisely. Always remember, hair industry is no magic. It is just simple chemistry at work.